The next concept that we have here is Euclidean spaces. So we are dealing with Euclidean spaces. This is nothing but a space. All right. This is pretty much a metric space. We are calling it as Euclidean space, where we deal with R, K, that is K dimensions. All right. K dimensions means R square will be metric space. All right. R cube will be 3D space. We know that, right? So this is the matrices basically. If you know the concept of matrices, you can able to understand that. Right? It is easy. Now, a definition is that since Rk, that is K tuples, all right, is there, where this Rk can be generated using this xi's, all right, where x1, x2, so on, xk are the real numbers, belongs to real numbers, all right, belongs to real numbers, and this Rk is generated using this, all right, sk. So we are saying that this this x's or xi's are the components and or the ith coordinates or ith components, and we can say that whenever we are getting this Rk by these sets, we will get vectors or points when this xk will be greater than 1, right? We're getting vectors or coordinates, all right? So there is a vector, all right? Here we have vector. Now if you're multiplying, this is a vector, right? There will be certain representation for a vector in a 2D space, right? Now if you're multiplying it with another scalar quantity, you will get this vector size increases, or sometimes if you subtract this or divide it, you can get the size of a vector decreases. So basically we can say that the Rk will have addition and multiplication of vectors applicable. Means we can do that. For example, if I consider a two-dimensional vector space that is x plus y, that is basically r power 2, all right? Now this is xi, this is yi, so you can write x1 y1 comma x2 comma y2 so on xk plus yk. Now if you multiply this x plus y with alpha, a scalar quantity, you can do that, right? Alpha x1, alpha x2, so on, alpha xk. You can do that. Multiplication you can do, and vector addition you can do. Vector addition, these two vectors are getting added. Scalar multiplication, you can do that in the space of Rk. Right. Now the next theorem that we are dealing with, let me take another paper for that. Okay, we have a theorem that says that under addition and scalar multiplication over the real field, we can have these axioms or the properties that we have to prove that if it is satisfy these properties, whether this Rk that you're considering is Euclidean space or not. All right, so for that we have some thing that we have to prove, that is it is plus addition is an abelian group. All right, So in abelian group is nothing but we have to prove five things. That is, we have to prove if we are considering this RK plus abelian group, then we have to prove it is commutative. We have to prove that it is associative. We have to prove that it is it holds closure axiom. We have to prove that identity exists, inverse exists. All right. So first, RK plus, we have to prove that it is abelian. RK plus, for example, if you consider, all right, sorry for the disturbance. Now we have to prove that this RK with the Euclidean space with addition modulo is an abelian group. So for that, we have to prove the certain condition of abelian groups. First, we have to consider that x and y belongs to RK. All right, we have already seen that x is nothing but xi's. All right, and y is nothing but yi's. All right, the x1, x2, x3, x1, x2, x3, so on. There is nothing but y1, y2, so on, yn. All right. All right. Now, first we have to prove the closure axiom. Closure axiom. For that, we have to prove that if we add with respect to addition, all right. So if we add these two vectors, that is x1 plus y1, comma x2 plus y2, so on. This goes on. All right. Xk plus yk, how much tuples we are considering, k up to k tuples. We have already seen that this x plus y belongs to Rk, so we can consider that it is a closure axiom since it is belonging back to the set that we have previously selected. This x belongs to Rk, y belongs to Rk. We get that both belongs to belongs to Rk, and we can say that it is closed. Now, second thing that we have to consider associative property. This Rk should satisfy associative law. X plus y plus z should be equal to x plus y plus z. That's it. It is pretty much easy. You can prove it. Now we have closure. So closure, I have already proved. Commutative law. All right, commutative law, where it says that x plus y should be equal to y plus x. We can easily prove that. Put x equal to x1 plus y1. All right, x2 plus y2, so on. Xk plus yk should be equal to y1 plus x1, x2, not x2, y2 plus x2, so on, yk plus xk. Since we have already seen that, since we already know that addition holds commutative property, we get that this vector addition also holds commutative law. All right, so we get this x plus y plus k. And identity, for identity, we know that when we multiply when we add 0 to other number, we get the same number. So this is the identity. We are getting the same number that we have previously selected. So in vector space, identity holds 0 is a 0 vector. We consider this as 0 vector. All right. Now one more last thing, that is inverse. We have to check that if inverse exists or not. So we know that we can write for example minus x plus x will give you 0 vector, right? We're just adding and subtracting x. So by this we can say that there is a vector here, minus x1 minus x2 so on, minus xk. If you're considering up to k tuples, you can add this with plus x1 plus x2 so on, right, plus so on, xk. Now if you consider minus x1, all right, plus x1 here, minus x2 plus x2 from here. Now by this we can get 0 0 0 so on, 0 vector. All right, so we have proved all 5 properties for the 5 properties of abelian group, and we can say that Rk satisfies this abelian group. It is an abelian group under addition modulo. Now next thing that we have to prove that if it is a Euclidean space, it should satisfy this property. That is, this is the second property. It should satisfy alpha x plus y should be equal to alpha x plus alpha y. For every alpha that belongs to real numbers, it belongs to real number, and this belongs to x comma y belongs to Rk. That is Euclidean space. So for that, it is pretty much easy. We know that. How do you write this? That is, first check this x plus y. Now you know that. How do you express this? x1 plus y1, x2 plus y2, so on, xk plus yk. All right, now if you're multiplying with alpha to x plus y, we are basically multiplying to each x1 y1, all right, plus alpha x2 plus y2, so on, alpha xk plus yk. All right, so we get that alpha x 1, we are just separating all these x1 x1 x2 xn xk up to xk, that is x1 so on xk, all right, plus alpha y1 up to yk. From this we get that if we take alpha common, we get alpha x, not taking out common, just replacing this x, because since we have to prove that this condition, sorry for that, you get alpha y1 alpha y. That's it, because we know that x equal to, since we x equal to x1 x2 so on xk, y equal to y1 y2 so on yk. If we consider z, then z1 z2 so on zk, sorry. These are all the vectors, right? Third condition that we have to prove that scalar addition, and then we are multiplying with x, and then what we have to prove basically is that we have to prove that alpha x plus beta x. This is what we have to prove. This is also pretty much easy. You just have to multiply alpha beta with x. We know that x equal to this one, right over here, this one, and just in place of x you have to write x1, x2, x3 so on xk. all right, we can multiply this each x's with alpha plus beta, x1 alpha plus beta, x2 so on alpha plus beta, xk. all right, from this we can have all alphas with x1 so on xk get, and from this all y's together, sorry, not y's, all x together up to xk with whenever we are multiplying with beta. From this we can have alpha x plus beta x. Alright, this is how what we got. This last fourth property, not last, we have one more property for that, sorry for that. We have alpha into beta x. Basically what we have to prove, alpha beta into x. So pretty much it is also similar to that. 1 into x, if I consider 1 into x, so you will get x. We know that 1 acts as a identity over here under multiplication modulo, and previously we have seen that under addition we have 0 as 0 act as an identity. All right, so this is pretty much Euclidean spaces. Whenever this Euclidean space is given, you have to check that all these conditions are satisfying or not. Let's sorry for that. Okay, no, I don't know whether this orientation is proper or not, but the screen rotation is getting changed frequently in my cell phone. I don't know what could be the problem behind it, but it is happening, and the lens is got dusty, so you're getting all this blur effect. Sorry for that, and hope I could rectify. Hope I could do something for that. All right, now we have one more thing, that is the concept of inner products. There is x comma x. This is inner product. This is nothing but we have x1, all right, we know that x1, x2, all right, x3, so on, xk is getting multiplied with another x1, sorry, comma, x2, so on, xk. That's it. So basically the inner product means this one, all right, and you can pretty much write all this as summation xi into xi, where I runs from 1 to k. You can write summation means we have series, all right, with xi and xi. If I are considering x comma y, 2 vector space, so you will have a series like this, summation I from 1 to k, up to k tuples, xi, yi, all right, where xi and yi are series, all right. So this inner product will also satisfy certain conditions. That is, it satisfy inner product will always be equal to or greater than 0, because since this x belongs to Rk vector space, so vector cannot be negative, so will always be positive or equal to 0, that we have already seen. So we know that from pretty much from that result that if a is greater than or equal to 0. Now we have another concept, that is x x comma x. If x comma x equal to 0, we get the x equal to 0, right? This is easy. If we have x comma y is given, we can have y comma x. It is also simple. We can say that it is a commutative property. And then we have also another, that is alpha x plus beta y comma z. Inner product of this will be equal to alpha inner product of xz plus beta y comma z, inner product of y comma z. It is simple. You can take this one and prove this one, all right. So alpha x1 plus beta y1, this is what it says, right, into z1 plus so on alpha xk plus beta yk. Okay. This is inner product, right? So we are just multiplying z1, z2, z3 and zk with all these. This is basically product, nothing else. So from this we can have alpha taken out separately, because each series will contain these alphas, all right. So x1, all right, and then this is multiplying with z1, all right, plus so on xk, this and this multiplying, right, zk. And for this beta we can take this out common for y1, z1, so on yk, zk, all right. So from this we can write alpha z inner product of, because we are getting multiplied, beta y comma inner product y comma z. Sorry for my handwriting, to be honest, all right. This is the some of the properties of inner product, so we have to keep that in mind, all right. Next concept that we have here is that we have a next concept, that is norm of x. This norm of x is nothing but it is equal to inner product of x with power of 1 by 2, or you can write inner product as previously seen. You can write xi, alright, xi into xi. That is what I have shown. Alright, since its norm is there, we have to add 1 by 2, so it will basically xi square and 1 by 2, it will become xi. So norm of x equal to this here, xi, summation xi's. So you have to keep that in mind. The norm of x will be equal to inner product of x comma x for basically it's 1 by 2 is nothing but root, right? And by using this, we have a theorem which we call Swartz Inequality, where it says that the summation aj bj square will always be less than or equal to summation aj square summation bj square. All right, where j runs from 1 to n, right? J runs from 1 to n for all j, for all j's, Now you have to prove this. For this, what you have to consider that if we say that this bj summation 0 equal to 0, so by this we can say that both sides, this left hand side and right hand side, will become 0. Okay, so we are considering that some relation that 0 will be less than 2 into b a j minus e b j square is greater than or equal to 0. Here b stand for nothing but summation bj's, right, square. A stand for summation aj square, and c stand for aj bj bar. One more thing that you have to consider here, understanding, that is whenever this summation bj aj bar is given, you can have bj bar into aj. All right, conjugate bar, it is nothing but conjugate bar. If we add conjugate to this, that is bj whole conjugate, all right, we get this conjugate, and this conjugate of aj will get cancelled out, and you will be left with this, right? You have to keep that in mind. And for this we have considered this, all right, sorry, this one. Take this one, that is the summation b aj minus c bj square, because we know that c aj minus c bj, if it is greater than 0, we can get from this here that from this we can get ab minus c square, that is greater than 0. We get ab will be greater than c square. All right, from this we can get ab, this one, ab and ab will be getting greater than, sorry for that if you have not seen that. If you consider this relation, from this we can get ab greater than or equal to c square. All right, so if ab is getting greater than or equal to c square, then we can say that this relation holds. All right, for that we have to, this is pretty much easy for multiplying, the normal multiplication. All right, where I have given the relation bar signatures. All right, so now this AJ, BJ, and this CJ belongs to complex numbers, right? Hence we are using conjugate bars, and this is pretty much simple. You can prove it. You just have to multiply this with this, and then this with this, then this and this, then this. Then you will end up having this one. That's it. From this you can get this one. From that you can have the question what is given. All right. So this is pretty much Swartz inequality. Okay. I don't know whether you might have seen it or not, but it is pretty much simple multiplication. You just have to use this BAG with multiplying with this, and then this get multiplied with this and this, and you have to use the concept of these bars, and then at the end you will end up having this AB minus C square. When we add C square to both sides, we will end up having AB squared than equal to C square. This inequality will act as a normal equal sign. All right, so don't get confused. You can either, in easy terms, you can write C square minus C square. If you send to other side, it will become plus C square. Right. So this is pretty much about Swartz inequality. All right. Next theorem that we have here is that the condition of norms that just now we have defined will also satisfy this. Will also satisfy this. Will also satisfy. This is modulus, not norm. X is scalar multiplication, and this inner product will be equal to. It will be equal to or less than norm of x, norm of y. All right, norm of x plus y will be less than norm of x plus norm of y by triangular inequality. This is pretty much easy. You can do it by yourself. Let me take one example here. The norm of x is equal to, you have known that you can write it as norm of xi square 1 by 2. All right, this property I'm explaining. So from this we get xi square equal to 0. We get xi equal to 0. That implies xi equal to 0. No problem. Where xi's are x1, we have already seen that, x1, x up to xk. All right, these will all vectors will become 0. Now if you consider alpha x, you will get summation of alpha xi whole square into 1 by 2. That will be equal to alpha square into xi square 1 by 2. You're just removing this alpha out of the alpha square. There is 1 by 2. Since it should be positive, you are adding modulus, and we are left with alpha xi square 1 by 2. We get alpha mod equal to norm of x, because we know that it is equal to norm of x, or this thing will be equal to inner product of x 1 by 2. That's it. So pretty much you can then do it by yourself, and this part right over here, this part right over here can be explained by using Swartz inequality. All right, that is what we have already seen, and this part right over here can be explained using triangle inequality. So pretty much this is easy. Okay, if you want, I can explain you for that. For example, we have norm of x plus y whole square. Taking norm of x plus y whole square, what do we have to prove? The norm of x plus y will less than norm of x plus norm of y. We have to prove this. For that, we have to consider norm of x plus y whole square. From this, we can write inner product of x plus y, that is whole square. We know that is power 1 by 2. These both will get cancelled out. We get norm of x plus y, comma x plus y. Alright, and from this we can have the norm inner product condition x comma x. Alright, plus x comma y. Alright, then y comma x, then y comma y. It is like a plus b to a plus b. That's it, with commas. Sorry, here we have plus, and from this we can write norm of x square to x comma y, comma y square. Alright, how do we get this? Since norm of x plus x will be equal to 1 by 2, we have that is equal to inner product of x. Sending this to other side, it will become x comma x equal to norm of x whole square. Alright, now we get this. Now from this you can arrange this y square plus 2 into inner product of x and y. Alright, now if you can see or observe that this looks pretty much like the formula for a plus b whole square. Alright, so you can replace it with norm of x plus norm of y whole square, and what we can have one minute. The inequality will change right over here when we are adding modulus over this. Alright, and modulus on both sides. Alright, so by this we can conclude that this part right over here is this part right over here, that is norm of x plus y whole square. Alright, square will get cancelled out. Norm of x plus y greater than or equal to norm of x plus norm of y. There is what we have to prove, and we got the same thing. Alright, so this is pretty much done. Now one more thing that we have to consider in RK, that is distance between 2 points. Okay, the distance between 2 points, this is nothing but distance between these 2 points. This is x, this is y. The distance between these points will always satisfy this condition x comma y greater than or equal to 0. D of x comma y will be equal to 0. D of x comma y will be equal to d of y comma x, and also this triangular inequality, d of x comma z plus d of z comma y, if x comma y comma z belongs to RK. So this is pretty much easy. You can do it by yourself. I will do one condition, is 4 conditions. For example, if I consider d of x comma y, and we have to prove d of y comma x. For that, what we have to do is that norm of x minus y, right, equal to norm of minus 1 into y minus x. Alright, it will become alright, this is small, we will get, hence we get y minus x. So since it's distance, we have to add modulus, and then this minus 1 can be taken separate out, and adding modulus will give you plus 1. this is pretty much about a Euclidean space. You have to remember this. And now I am going to move to explain the concept of matrix spaces. Alright, this is the main concept where we are using all the conditions that we have proved previously. Will help you more understand the concept of matrix spaces. Basically, matrix spaces satisfy all the conditions that we have seen previously. Now, in matrix spaces, okay, I'm going to continue that in next video. Thank you for watching. Hope you like my video.